Hello there, students. There's a problem, and it's called the tangent line problem. Demonstrate, let's look at a curve. This is just your everyday basic parabola. Now let's draw a line that touches it at, this point. This line is called a tangent line. The word tangent comes from the Latin word for touch because the line intersects the graph at only one point, touching it. Now, what if we wanted to find the equation for this line? How would we even do that? Well, the answer to that question leads us to a fundamental concept in calculus, the derivative. Now, there are two things we need to know in order to write the equation for the tangent line, the slope and the y-intercept. And generally, if we figure out the slope, we'll be able to find the y-intercept with some simple algebra. But what is the slope? Now, let's start with the plain old slope formula, the change in y over the change in x. Might have learned it as rise over run. To find what the changes are, we'll do a little illustration. Now, say that we have a line that intersects the graph at point A and point B. We can easily figure out the slope of this line if we know the coordinates of the 2 points. So how do we apply this to our tangent line problem? Well, notice that if we move point A closer to point B, the line between them starts to look more like the tangent line at point B. So hypothetically, if point A was infinitely close to point B, the line connecting them would basically just be the tangent line. But before we get too excited, we also need to note that the changes in y and x get infinitely close to 0. So the slope formula essentially becomes 0 over 0, which isn't really a thing. But don't worry, not all hope is lost, because there's a tool that allows us to handle these kinds of situations, and that's the limit. Basically, what a limit does is it tells you what a function of x does as x approaches a certain value. Comes in handy when a function isn't defined when x equals the value, which, as we'll see, is exactly what we need here. So let's look at the points A and B we had before, and we'll look at them another way. So let's say the x-coordinate of B is separated from A's by h units. Now we can write our slope formula in terms of x and h. And to show point B getting infinitely close to A, we take the limit as h approaches 0. And the result of calculating this is another function of x, which we call the derivative of f of x. But how can you actually calculate derivatives? Well, using that limit definition I showed you earlier, some very smart people figured out some simple rules that you can use to find the derivative of a function. First, you'll need to know that we find the derivative of each term of a function separately, so keep that in mind when you need to break down a problem. And there's also a rule called the constant multiple rule, where if you see a function of x multiplied by a constant, you can just pull the constant out, take the derivative of the function, and then multiply the derivative back by the constant. The first and the most basic of the rules is the power rule. Now basically whenever you see x raised to a power, you multiply by that power and then subtract 1 from the power. Simple as that. And from the power rule also comes the rule that states the derivative of a constant is 0, and the same principle applies to things like square roots and negative exponents. And then there's the product rule. You can use the product rule whenever you see two functions of x being multiplied together into one big function. The product rule says that the derivative of the whole function is the derivative of the first factor times the second factor plus the first factor times the derivative of the second factor. Seems like more to remember, but if you just keep in mind that the two factors are taking turns getting differentiated, it makes it a little easier. And then there's the quotient rule. This is the big one. You use it when you see two functions of x being divided. The exact formula is this, but people often use a catchy mnemonic because it's, really long. And if you call the function in the numerator high and the denominator low, then the formula said out loud is low d high minus high d low all over low low, where d high is the derivative of high and d low is the derivative of low. It sounds stupid, but hey, if it works, it works. But just remember the two terms in the numerator are subtracted and the denominator is squared. There's another very helpful rule called the chain rule, and we use the chain rule to find the derivative of a composition of functions, where the output of the inner function becomes the input of the outer function. This is the formula, but I like to think of it as a siege on a castle. Now say you have the derivative battering ram diagram, and the castle has an outer and inner gate representing the two functions. First, you break down the outer gate, which basically just means take the derivative, but the inner gate is left untouched. But then you break down the inner gate too, and then you just have to remember to multiply those two factors together. Those rules will help you find derivatives of basically any function with polynomials in it, but there are also some special functions whose derivatives we need to know as well. One of these classes of functions is the trig functions, like sine, cosine, and tangent. You will need to remember that the derivative of sine is cosine and that the derivative of cosine is negative sine. Do not forget that negative. And as for the other four trig functions, you can express them all in terms of sine and cosine and then just use other rules. For example, tangent is the same as sine over cosine, so you can use the quotient rule on it. The hyperbolic functions work the exact same way, except you don't even have to worry about cosine having a negative derivative. And then there are the exponential functions. The one you really need to know is the derivative of e to the x, and it is, this will blow your mind, e to the x. Yep, that's right. The derivative of e to the x is itself. And it's the only important function with that property. That's why e is a cool number. But what if you want to find the derivative of something like 2 to the x? You can just replace the base with e to the natural log of the base to make the calculus easier. Then you can just use the chain rule and not have to worry about the weird base. That's why e in the natural log appears so often in science. Not because e has some deep physical significance like pi does, but because the calculus is so much easier. And then there's logarithms. All you really need to know is the derivative of the natural log, which is 1 over x. For a logarithm of any base, you can use the change of base formula to turn it into a natural log over the natural log of the original base. Then you can work from there using the derivative of ln and the quotient rule. And now that you know how to find derivatives, you might ask yourself, what if we took the derivative of a derivative, or the derivative of a derivative of a derivative for that matter? It sounds dumb, but it's actually a very important concept. Higher order derivatives. The classic example of this is in physics, more specifically kinematics, or the study of motion. Say you have a particle whose height y is given by this quadratic function of time. If we want to find its vertical velocity, that's the rate of change of its height, which is given by the derivative of y. But we can also find its vertical acceleration by taking the derivative of that. Mathematically, we would call this the second derivative of y. We can write the nth derivative of a function f like this if it's the fourth or higher derivative. For the first, second, and third derivatives, we just write the appropriate number of prime symbols. This is one way to write it, but we'll be looking at other ways soon enough. Higher order derivatives are everywhere in science, and they'll also be useful when you get to power series later in calculus. Now, about those other ways of writing derivatives. There are two that you should know. One is the Leibniz notation, which imitates the slope formula. It's very useful for when you start solving differential equations, and we'll be seeing it in action in a moment now when we learn another cool technique. And the other is the Newton notation, where you write n dots for the nth derivative of a function. It shows up a lot in science, but you don't really use it in pure math that often. With that cleared up, let's go into another technique. Consider the equation for the unit circle. Now, what if you wanted to find its derivative? You might think to solve for y and then find the derivative, but you'll end up with a plus or minus sign, and it's unpleasant. Instead, we'll use something called implicit differentiation. First, I'll need to clear something up, and that is which variable you want to differentiate with respect to. Usually we differentiate with respect to x, so that's what we'll do, which means all of our standard derivative rules get applied to x. The first term, x squared, is easy enough to differentiate. The derivative is just 2x by a simple use of the power rule. But what about y squared? As we said before, we're differentiating with respect to x, not y. However, even though the equation doesn't explicitly state it, y is an implicit function of x, which means we could write y explicitly in terms of x if we wanted to. But we don't even have to do that. If you remember, the chain rule allows us to find the derivative of compositions of functions. Now, how does that apply here? Since y depends on x, we can rewrite the term as y of x squared, which actually makes it clear that we can define inner and outer functions and then use the chain rule. Without finding the derivative of y of x, we can just write it as dy over dx, using the Leibniz notation we learned earlier, and the derivative turns out to be 2y times dy over dx. And if you don't want to go through the mental gymnastics every time, just take the derivative with respect to y and then multiply it by dy over dx. And as for the right side of the equation, remember that the derivative of a constant is always 0. Now we have 2x plus 2y times dy over dx equals 0. And now we have the ability to solve for the derivative in terms of x and y with just some simple algebra. And see how nicely that works out? Yeah, pretty. Now with implicit differentiation stored in your old noggin, you'll be able to comprehend derivatives of inverse trig functions like arcsine and arccosine. Now consider the function y equals arcsine x. We have no idea what the formula for the derivative is, so we can't just plug and chug. But we're smart, so we can figure it out ourselves. Even though we don't know how to differentiate arcsine directly, we know how to differentiate sine. So it's helpful to rewrite the equation as sine y equals x, which we just get by taking the sine of both sides. The only problem is that y is no longer explicitly solved for x, so I need to use implicit differentiation. If we take the derivative of both sides with respect to x, it turns out to be cosine of y times dy over dx equals 1, so dy over dx equals 1 over cosine y. This is all right, although it would be helpful if the derivative were in terms of x and not y, if we want like a rule for it. So we rewrite it as 1 over cosine of the arcsine of x. It's really hard to read, with a simple substitution. Surely, though, there must be an easier way. Let's switch gears to the unit circle for a moment, and we'll draw a quick triangle. The arcsine of x is the angle with the sine of x, which we'll just label as theta. But note that the length of the vertical side of our triangle is equal to x. This is very important. The arcsine function of x results in theta, so now we're just interested in finding cosine theta. This is the horizontal side of the same triangle. But we know that the vertical side is x units long and that the hypotenuse is 1 because unit circle. So it's literally just the Pythagorean theorem, and the entire expression cosine arcsine x in the denominator simplifies to the square root of 1 minus x squared. So the derivative of the arcsine function is indeed 1 over the square root of 1 minus x squared. And just a little nuance, note that this is only real and defined when the absolute value of x is less than 1. QED. Now you can do the same thing for any of the other inverse trig functions. You can even do it for inverse hyperbolics, although you need to use this thing instead of the unit circle, and I don't know how to do that. Or you can just memorize the formulas if you want. Anyway, that's derivatives for you. Hope this cleared things up. I would really appreciate if you like and subscribe. It does help my channel. And feel free to comment any questions, and since I'm supposed to be doing music, I might think about making songs about this kind of stuff in the future. Might be interesting to see how that works. Anyway, see ya. So after I edited the video, I realized I left all of you without any worked examples on how to solve or calculate derivatives. And I'm sorry about that. So I'm going to do some right now. So let's start with the function x to the x. This is a classic advanced derivative finding problem. And it looks really confusing and weird because it is. But as long as we just do what we've been taught, we know we're supposed to replace the base with e to the ln x, and we have this. So now we use the chain rule. We can define an outer function e to the x, inner function is x times ln x, and then we differentiate our outer and inner functions, and that will allow us to just plug straight into the chain rule. And if we do that, we find the derivative as x to the x times the quantity ln x plus 1. Simple enough. Now here we see another problem, and that is cosecant cubed of x. So the first thing we see is just chain rule, because we're taking function of a function, cosecant cubed. So the outer function would be cubing, and the inner function would be the cosecant of x. So after we just differentiate our inner and outer functions, remember that cosecant is the reciprocal of sine, so you use the quotient rule to figure that derivative out. And then we can just plug straight into the chain rule, and we end up finding the derivative as -3 cotangent x cosecant squared x. Okay, the next problem we have is log base x of pi. So there are two things that might worry you here. First is base of x, that's obviously pretty strange. And the second is maybe pi, although if you just keep in mind that pi is a constant, it's really not that bad. But just remember as far as the log base x goes, just remember you use the change of base formula. Just remember how to do that, and we find that this logarithm is equivalent to ln pi over ln x. And of course, this is pretty straightforward using the quotient rule. And we find the derivative as -ln pi over x ln x squared.